All right, so let's start with a discussion on how you bring up that model which reduces to the logistic equation. So take a moment to write this down, but while you do that, let's go over the elements here. So like I said before, in our simplest setting, suppose you have just infection and recovery, no immunity, just back and forth movement from susceptible to infected and from infected to recovered. And again, assuming the population is well mixed, that justifies this format of the infection rate. So when you build the equation in a model, you essentially say in each rate of change, in each derivative, what comes with a plus sign and what comes with a minus sign. So any transfer from one class to another means a quantity leaves an equation and comes in the precise form in the other equation. So if lambda Si is that many infected people per unit of time, new infected people, that many people leave the S class and get into the I class. Minus here, plus here. The recovery rate, which is given as a per capita rate, moves back from I to R. So we don't need to do any math to realize that the total population is constant. If you build the model and you don't make any biological mistakes, so to speak, in the equations, stuff like that, like whether the population is constant or not, is going to be obvious from the beginning. There's no gain or loss in the total population. There's no death, no additional population coming from the outside. But whenever in doubt, you can add the two equations. And this, by the way, could be a check to see if your model doesn't have a flaw. We'll talk about flawed models later. But I mean, if you know that your population should be constant, if your modeling makes sense, then if you add the two derivatives, the equations should cancel out. Because constant population means that the derivative of the total population should be 0. So that means, so if S plus I prime is 0, that means S of t plus I of t equals n, which is some constant. Obviously positive. So that allows you to write the system of equation in terms of a single equation. Because, for example, if you take the second equation and replace S with n minus I, that gives you a single differential equation in I of t. And this is the point, or the part in which you have to make some connections with the logistic case. Again, if you forget about the logistic equation connection, you can just do the phase analysis. Right? You can factor I. So you have lambda n minus lambda I minus R times I, set it equal to 0, and find the equilibrium points. One of them is 0. The other one, if you actually solve for this, this will be lambda n minus R over lambda. So you could do the phase analysis, or you can compare it with the logistic equation. So I'm not going to do phase analysis right now. I just want to show you how your equation, sorry about that, made a mess here. So how this equation actually compares to the logistic one. Well, if you look carefully, again, if you distribute these constants here, so you have lambda n I minus lambda I squared minus Ri, and if you factor I, you should basically recognize it with what I talked about in the previous part as equation of that form, which suggests logistic equations, especially if b is greater than 0. Because if that's the case, then you know from the logistic equation that if a is less than 0, x approaches 0. If a is greater than 0, x approaches the positive equilibrium, which is a over b. So it's out of range. Okay, so if a is less than 0, x approaches 0. A greater than 0, x approaches a over b. So again, you should think about the logistic equation each time you see essentially an expression of that form, a constant times x minus a constant times x squared. So like I said, with a little bit of practice, I can basically tell just by looking at the equation in this form that I of t is going to approach a positive equilibrium point, which is lambda n minus r over lambda, if lambda n minus r is greater than 0. Because the coefficient of I plays the role of this coefficient in the logistic equation. With a little bit of rearrangements of the terms here, you can literally write this in the standard form of the logistic equation. So for example, if you really want to, since the logistic equation in P, the standard one was written like this, and again, remember, in that discussion, R was greater than 0, K is greater than 0, I can actually do this work for my equation in I. You don't have to, but I just want to make it the point how this compares to this. I can, for example, pull lambda n minus r, keep it together so that it's out like this. And then inside the parentheses, if I pull I as well, there's just 1 minus, let's see, lambda I over lambda n minus r, I, and I can further write this down as lambda n minus r, 1 minus I over lambda n minus r over lambda. Right? So I just want to emphasize that in the standard equation that we studied before, the role of little r is placed or replaced now by lambda n minus r. And the role of this carrying capacity is replaced by lambda n minus r over lambda. Now you don't really have to do that. All you have to do is to basically recognize that what you have here is essentially a logistic equation and realize what is the part in the model that plays the role of R, which is crucial in understanding whether the population approaches the constant, the positive constant, or a 0. Now, this, we can do it this way, or you could just simply do the phase line analysis like I mentioned before, which is also straightforward, like I said. You have the two equilibrium points, and then you can do the phase line analysis. What is important here also to understand is that you have a discussion, right? For example, the sign of lambda n minus r is important, right? Because if it's negative, then the second equilibrium point has no biological meaning, right? Because you don't have negative population. So let's do this on the second page. Let me actually rewrite this on the second page. So the equation in I, let's write it like that. So like I said before, we know that if lambda n minus r is less than 0, then I of t approaches 0 from what we discussed in the logistic equation. And if lambda n minus r is positive, we can show that I of t approaches lambda n minus r over lambda. Okay, so what this has to do with the logistic equation in terms of limited resources? So basically, this second part of the result, right, says that, well, if you have this condition, the infected class is going to approach some positive limit. Okay, so a similar graph to what we had in the logistic equation. And in that case, the interpretation was, well, we have limited resources. At some point, there's an inflection point after which the growth slows down and it approaches a positive constant. So this is the graph of I, and this is the lambda n minus r over lambda. Well, in the context of an infectious disease, limited resources for I of t means fewer people to infect. So for the epidemic to grow, you need to have enough people to infect. All right, so this is why, which is kind of cruel if you think about, but resources for the infected class, if you think about from the point of view of the infection, means do you have enough susceptibles to sustain the growth? Which is the reason why they call about, we'll talk about the herd immunity later, but that's the reason why if you have lots of infected people in the population, the infection rate slows down actually, because there's not that many people remaining to be infected. So you see that what we call about carrying capacity and limited resources can mean completely different things in different contexts. So in this case, we still have mathematical logistic model, but limited resources essentially means do you have enough people to infect or not? And then the difference between whether you approach a positive constant or zero depends on the sign of a constant, and that can be interpreted biologically further, right? So for instance, does it make sense that the infected class goes to zero if lambda n minus r is less than zero? Well, think about what this inequality essentially suggests. It says basically that the recovery rate should be greater than some constant. If it was the opposite, you should realize you made a mistake somewhere, okay? Because it would make sense that the infection goes away if the recovery rate, which is against the disease, basically, right? It's like a death rate for the disease, if you want, was less than something. So stands the reason that the condition for I of t to go to zero is recovery greater than something. And we'll spend a lot of time actually interpreting these conditions. I mean, you could basically, again, write the whole thing as a comparison with 1. So you could think in terms of how the infections reproduces itself. We'll talk about the concept of reproductive number later. But I want to pinpoint what we talked about in the previous week, the meaning of the removal rate. So the meaning of the inverse of the removal rate. So remember what I told you before, the inverse of the removal rate is essentially the expected time spent in that category. This is a removal rate from the infected class. So 1 over r is basically the time as being infected. It's the estimated time of an infectious individual staying infectious. So 1 over r is how much time is spent in infectious status. So this quantity here basically says, because lambda n basically is the number of people infected. Well, I don't want to jump ahead too much here, but if you imagine that nearly everybody is healthy in the beginning, that means nearly everybody is susceptible. So that means if you drop 1 infectious individual, that's how many infections will be produced because of the meaning of lambda si. We'll talk about that later. And so that's per unit of time, and if you multiply by the time infected, this whole quantity essentially tells you how many infected new infections are created by 1 infectious individual in a healthy population. And so again, if that's less than 1, you would expect that you don't have an epidemic, it will die out, and I of t goes to 0. And if the opposite condition happens, then of course the infected class approaches a positive quantity. The inflection point in this context, so the inflection point is that sweet spot in which the infection slows down, still increasing, but at a slower and slower rate. So when they have these measures, for example, with flattening the curve or whatever they want to call it, that's, you know, different context, you know, what what you want to do. But when they look at the dynamics of the infections, the peak essentially appears around this inflection point. So it's the point of the highest growth, right? I mean, the growth is nearly exponential up until this point, and this is the sweet spot which gives you the maximum of the growth rate. So that's why they say it's a good sign, even though you still have lots of new infections. But if they notice this sort of inflection point in which the new cases start to be lower, this is essentially the sign that you passed the peak. This is just in this simplest context, because in a more complicated models, it's a little bit more difficult to illustrate this by a single inflection point. In a single equation like this. So to summarize, make sure by this point you know very well how to do the phase line analysis. Make sure you can recognize the logistic equation in different contexts, and even if you don't, be prepared to do the phase line analysis if that fails. I'm saying that you should recognize it because, again, like I said before, once I actually match this with the logistic case, if I look at the coefficients here and I said, okay, this is positive, just like in the logistic case, the coefficient of p squared, this basically plays the role of r in the logistic equation. So I know already that if this guy is positive, I'm going to stabilize at a positive equilibrium point. And so notice these are in agreement, right? So if this is positive, this is also positive. And if this is negative, that's going to go to 0. The initial conditions in this case, by the way, is always between 0 and k. I forgot to mention this because, again, that's the only biologically correct assumption. Since I have k number of people to begin, n, right? N number of people to begin with. Total population is constant. In the way the model is built, you can only have a number between 0 and n for the initial condition. So you're not allowed, even though the math won't be upset, right, if you do it, but you're not allowed to plug in anything outside 0 and n because that's the assumption made in the model. So I think that's it for this week. We'll continue obviously next week with other topics. See you later.